Hello and good day everyone. Our presentation is titled Real-Life Applications of Differentiations and Integrations for the course SM14103 Mathematics 1. This presentation is prepared for Dr. Kariza Ghazali. In these presentations, we will explain how differentiations and integration is applied in real-life situations, specifically in the science field. These are the members of our group. I am Edrina Elvi binti Madrin, followed by Farlan Ivy Felix, then Aishi Batrisha Putri binti Ahmad Fansuri, and Muhammad Irfan Izzat bin Marib. Each member contribute to the discussions and solutions of this problem. In this slide, I will explain about the problem statement. This problem is a real-life applications of differentiations involving cancer tumor growth. The volume V of a spherical cancer tumor is given by V equal to pi x cubed over 6, where x is the diameter of the tumor. The physicians estimate that the diameter is growing at the rate of 4 mm per day, at a time when the diameter is already 10 mm. The question is, how fast is the volume of the tumor changing at that time? Next, in this slide, we will explain about the understanding key concept and rule. The first one is about volume of sphere. The volume V of sphere is given by the formula V equal to 4 over 3 pi r cubed, where r is the radius. In this problem, the volume is given in terms of the diameter x, where V equal to pi x cubed over 6. Moving to the second one, which is the related rate. This problem involves related rate, where we need to find the rate of change of the volume with respect of time, given the rate of change of diameter with respect to time. So, we will use calculus, which is a chain rule, to relate this rate. Next, the third one is the chain rule. If V is a function of x and x is a function of t, then dv over dt equal to dv over dx multiply with dx over dt.
So, to solve this problem, first we should take note on the given information. We know that V is equals to pi x to the power of 3 over 6, and we know that dx over dt is equals to 0.4 millimeter per day, which is the rate of change in diameter. We know that x is equals to 10 millimeter, which is the diameter at a specific time. Hence, what we need to find is dv over dt, which is the rate of change of volume. So step 1, we should differentiate the volume equation with respect to x. V is equals to pi x to the power of 3 over 6. So dv over dx is equals to d over dx times pi x raised to the power of 3 over 6, which is equals to pi over 6 times 3x squared. Hence, dv over dx is equals to pi x squared over 2. So for step 2, we can use the chain rule to find dv over dt. So dv over dt is equals to dv over dx times dx over dt, which is equals to pi of x squared over 2 times 0.4. In our step 3, we should substitute the given value of x equals to 10 mm into the equation. dv equals dt is equals to pi times 10 squared over 2 times 0.4, which is equals to 50 of pi times 0.4, which is equals to 20 of pi. So, the rate of change of the volume of the tumor is 20 pi cubic millimeter per day.
Okay, in this slide, we look at a real-life application of integration using a flu epidemic example. I will read the equation first. A flu epidemic hit a town. Let Pt be the number of persons sick with the flu at time t, where time is measured in days from the beginning of the epidemic and P0 equal to 100. After t day, if the flu is spreading at the rate of P prime t equal to 120 t minus 3 t squared people per day. The question is, find the formula for Pt. Okay, in this slide, we need to the understanding the key concept here have five key concepts. First, rate of change, also we know as a derivative. Let's start with the derivative. We use the p prime t to represent the rate of change in the number of people who are sick at time t. In simple words, this tells us how fast the number of patients is increasing or decreasing each day. If many people are getting sick quickly, the rate of change is high. If fewer people are getting sick, the rate of change is lower. Second concept, original function, which is integral. Now, what if we want to know the actual number of sick people, not just the rate? So, to find the PT, we need to use the integration. Why? Because integration is the process of reversing the differentiate. So, when we integrate the rate of change, we recover the original function. Third key concept is constant of integration. Constant of integration. When we integrate a constant called C always appear. This happens because many different functions can have the same derivative. So we need more information to find the exact value of C. Fourth key concept is initial condition. This is where the initial condition is used. For example, if you are given p0 equal to 100, this means that at time 0 there was 100 patients. We use this information to calculate the value of C, ensuring that our function pt correctly represents the real situation. Okay. Uh, the fifth, behavior analysis. Finally, let's analyze the behavior of the function. If p prime t is positive, the number of patients is increasing. If p prime t is negative, the number of patients is decreasing. If p prime t equals 0, the number of patients reach a maximum or minimum. So, this key concept help us understand when the disease is spreading and when it starts to slow down. So, by the understanding the derivative, integral, and initial condition, we can use the mathematics to analyze real life situation. Okay. In this slide, we need to focus on the mathematical rule used to solve the problem. First, basic integration rule. First, we need to remember some basic integration formula. When we integrate a constant, for the example, integrate a dt, we can get the a t. When we integrate a power of t square, for the example, integrate b t square, we can get b over 3 t cube. Uh, this this rule allows us to find the original function from its rate of change. Okay, second mathematical rule is use initial condition. After integrating, we always get a constant of integration called c. So to find its value, we use to the initial condition. So we substitute t equal to 0 into the function and match it with the given starting value. So this ensures the model fit the real situation. The third mathematical rule is consistency with unit. We need to must check the unit. Time is measured in day. The rate of change is measured in a people day. So keeping unit is consistent help avoid mistake and ensure correct interpretation of the result. Finally, we do a logical check. We ask ourselves, does the function pt make sense? Are the values realistic? For example, the number of people cannot be negative. If the result does not make a sense in real life, we need to recheck our calculation.
The given information from the question is P of 0 equals to 100, which means at the start of the epidemic, 100 people are sick. P prime of t equals to 120t minus 3t squared. The number of sick people changes at this rate per day. T equals to time in days. It is measured from the beginning of the epidemic. P of t is the total number of people sick at time t.
So the solution is we start at step 1. Since p prime of t is derivative of p of t, we can find p of t by integrating p prime of t. Lastly, we will get pt equals to 60t squared minus t cubed plus c. From the step 1, we go to step 2. Since we know that p of 0 equals to 100 and we let t equals to 0, and so we have to take 100 into our integration to find the constant c, and we found out that c is equals to 100. So the answer for finding p of t is equals to 60t squared minus 3t squared plus 100. The conclusion is, since p prime of t represent the rate of change of the number of infected people, the function p of t can be obtained by integrating p prime of t. Using the initial condition p of 0 equals to 100, the formula for the number of people sick with the flu after t days is p of t equals to 60t squared minus 3t squared plus 100.